So when exactly to use the unit and what exactly is the unit designed for? Hello and welcome everybody, it's Imad here, and by the end of this video you're going to be able to train your own unit model on your own data. I'll provide you with the Google Colab and everything you need. But first, let's have some theory. Alright guys, so before we get to the Google Colab and the actual training of the unit model, let's first have a quick overview of what is the unit model and when do we exactly use this model and why. So when to use unit? We use unit whenever we want to generate a new image that retains the spatial details of the original image. So a very good example for this is image segmentation or heat maps. So if we look at this picture over here, let's assume that this is an image segmentation. We are changing the colors within the spatial details of the original image. So before we dive into the mechanism of the model, I just want to show you some of the models that use this structure. So unit is used by some of the most powerful models out there like Stable Diffusion, DAL-E, and Pix to Pix. Alright, so let's dive into the architecture of the model. And in order to do that, let me remind you again that we use unit whenever we want to retain the spatial details of the image and be able to see both the big picture and the very fine details, and everything in between. So let's have an example. Let's assume that our target is to recognize that this is a tire of a bicycle. So first we need to see the big picture over here, that this whole thing is a bicycle, and then we need to be able to see the finer or the smaller image over here and recognize that this is a tire. Otherwise it could be a tire of something else. Alright, so on the left hand side we have the encoders over here, and on the right hand side we have the decoders. So how is the unit able to see both the high level or the big picture and the very fine details and everything in between at the same time? Encoders work by downsizing the image. So, for example, if the image was 512, it will go down to 128 and then to 64 and so on and so forth, depending on the architecture and design of the structure. On the other side, the opposite will happen. The decoders will start to upsize the image back to the original size. So, the features extracted from the first encoder reflect the very fine details of the image, are computed based on the very fine details of the image. Now, the features extracted from the next encoder reflect a more zoomed out portions of the image. And the next decoder will reflect a more and more zoomed out bigger picture of the image, and so on and so forth. Now the magic happens in those skip connectors. They are called skip connectors, which is the act of taking the extracted features from the encoder over here and plugging it right into the decoder that's responsible for generating the final output. So this is the magic trick that will make the model able to sustain and retain the spatial details of the original image. Because if we did not plug those extracted features right into the decoder, most of those features and details will be lost within the encoding decoding process. And again, this is how the model is able to take into account both the features of the very, very fine details and the features of the big pictures of the image and the features also in between. Alright guys, so enough with the theories and let's dive into the code. So by the end of this video, you should be able to train your own unit. I'll provide the link to this Google Colab and it will be available for you to use it if you wish. Alright guys, so in order to train the model, you're gonna have to run those 5 cells over here. I've arranged them for you from 1 to 5. The first one is the model design. First, let me jump to the build function, which will build the model. We have
4 encoders in our design. It doesn't have to be 4. Okay, and we have 4 decoders over here. So the output from this encoder will be plugged, okay, into the input of the next one, and the output of this encoder will be plugged into the input of the next one, and so on and so forth. Okay, now let me show you the skip connectors and how they are reflected into the code. Okay, each decoder over here will have 2 inputs. One is the S1, which is the output of an encoder over here, and its normal input. Okay, so the decoder will concatenate, if I pronounce that right, okay, those two, and produce the output. All right, so in my case, I have one output channel, one analog output channel, and I use sigmoid for the activation. Okay, so make sure, and those are the designs of the decoder and encoder blocks. Okay, and the convolutional block. Okay, here, okay, we have the learning rate. Okay, you can start with an appropriate learning rate, and you have also the number of epochs. Okay, those are the width and the heights of the images for the training data in my situation. Okay, I also used a batch size of 2 because, you know, the memory at Google did not really allow for more. So now the big question is, where do you place your data in order to train your own model? So let's look over here. I have my drive, and a folder called unit. Okay, so make sure that the link to this folder, okay, copy path, okay, is defined into this cell 1, line 33 and 35. Just paste the link to whatever folder you have created, okay, into those 2 lines over here. Okay, and your training data will be inside this folder. So your data should be divided into training data and validation data over here. Now let me remind you that your data will be input images and output images, right? The output images are called masks. They like to call them masks, right? And as well, the validation data will be input images and output images, or output masks. So now the name of this folder, which is inside the unit, is specified here, and the folder containing the input images, okay, will be specified over here. Okay, so this folder is inside this folder, and inside the folder you have specified in the upper cell. Okay, the same thing, your masks will be in a separate folder. Okay, and this is the name of it, and this folder will also be in the train folder. Okay, and this will be also in that folder. So let me show you this folder really quick. So this folder includes the training input images, and this folder, let's see it over here really quick, includes the output masks for those training images. All right, in my case, the size of the images is 1024. Okay, you can change that to fit your needs, but I think it should be the multiples of 8. Okay, like 64, 128, and so on and so forth. So in order to create your own model, you can change this architecture over here. Okay, you can change, add layers, remove layers, whatever you want. You can modify the activation functions, the filters, whatever it is that suits your needs. Okay, you can modify the learning rate and the training parameters, and number of epochs, the size and width of the input and output images, right? And now you will bring your input output images, and you will divide those training data into validation and training, okay, and then you will place the input images into a folder and specify that folder over here, okay, and that folder should be inside the train folder or whatever you have created, and you will place the output images of those input images in a different folder, and you should specify the name in this line over here, and it should also be in the train or whatever you have created. The same thing happens for the validation data. You will place the input images of the validation data into a folder like this, and this should be inside the valid folder or whatever you have created for it, and the same for the output images. All right, so now you have modified the model architecture to suit your own needs. You have created the folders and divided your images among all those folders. Okay, so you will run this cell and you will run this cell over here, and then you will just run this cell, which is compiling the model. In my case, I have used the mean squared error because I'm training for an analog output values for the pixels. Okay, you can also render some other metrics like the mean absolute error. All right, so let's talk about the callbacks really quick before we move on. Right, this line over here is to reduce the learning rate, okay, during the training process based on a certain criteria. Okay, you can define what it is that you want to monitor and base your reduction on. In my situation, I have selected to reduce the learning rate based on the loss of the training data. Okay, and it is reduced to 1% of the previous training rate. If the patience is 24, it means that the model will wait for 24 times, and if no improvement above a certain threshold is achieved, it will reduce the learning rate. Okay. Right, and then you run the training instruction and start the training process. After the training, you will have your checkpoint, okay, whatever it is. By the way, the link to the checkpoint which will be produced is defined here. Let me show it to you. This is the link to the checkpoint. Okay, what is the file directory? So it will be inside this directory. Okay, and this will be the name of it, and this will be the CSV file about the training process. So after training, you will have this checkpoint inside the unit folder. Okay, and now let's do some inference. Let's evaluate some output based on some inputs. So you will run this cell where you will load this checkpoint which you have created in the training, and then here you will have the link to the input image. Okay, so you will have the link to whatever input image that you want to evaluate, and then you will run this line, which is the model predict. So you will define the input image you want to do the inference on, and you will run this cell, and then this cell will show the image for you. In my situation, it's a grayscale image. Okay, so if you are not working on a grayscale outputs, you might want to modify this to suit your situation. Okay.
Thank you guys so much for watching. I wish that this was helpful for you, and please subscribe if you want more of those videos.